thanks for the introduction. So I'm Jorden. I'm doing a double major in information system analytics, teach blockchain in SMU. I've done a lot of cybersecurity stuff from pen testing, and I recently finished a CSA internship on pen test. So what am I here to share? So some of you may hear that, blockchain, this is a buzzword. Some of you may find it's a bit foreign. Like, I hear it, but I don't really know what it is. Some of you may have even heard that it's unhackable. But honestly, it's not that different from traditional attack vectors from normal systems. So what I'm here to show you today is a compilation of various attack vectors on 3 different levels: the smart contract, the consensus mechanism, and the telecommunications topology attacks. And I hope you guys really take home something new, and I hope I can add value to what you guys know already. So moving on, for the uninitiated, what is a blockchain? So essentially, a blockchain is a special kind of database. Traditionally, we have centralized databases. Let's see if the laser is working. Oh wow, it's working. So for example, your AWS node, every information has to go to a central point, and then it returns back to you. Then increasingly, we've seen a shift towards decentralized nodes. So what happens is, this is for example in YouTube, where instead of making every request go to the HQ in America, they set up different nodes everywhere. And all of this go back to a central node. So this is the concept of decentralized nodes. And blockchain essentially is a distributed ledger. So what that means is the first thing you would see is that every node is interconnected to another node. That means there's a direct access from one node to another. Over here, in order to get from this node to here, I have to go through a centralized point. Over here, I can just go directly. So this brings out a lot of benefits. So one of the benefits is data integrity, where the consensus, because all of the nodes are interconnected to each other, they can verify data, and they can reject nodes of inconsistent data. As such, you will need to manipulate or hijack about 51% or 33% of the nodes to execute attacks, depending on the consensus mechanism. There's high availability, because now, even if I am able to disable one node, I can always get rerouted to another node. And it's also harder to DDoS a network when there's no single source, there's no central point of failure. The distribution of bandwidth is also a concept that could potentially help to mitigate DDoS. This is already done in Cloudflare CDNs. So high auditability is another benefit, not so much security related, but more on the fraud area. So information in the blockchain is transparent to all nodes in the network, because everyone is connected to each other, everyone can see the information there, and we can really, it's all linked to each other. This forms a chain. So that's where the chain in the word blockchain comes from. So let's talk about smart contracts. And smart contracts are basically cryptographic computer protocols that is designed to facilitate, monitor, verify, and enforce performance of agreements, aka contracts, but not in the legal sense, in an immutable and exact manner, which is whatever is coded in the contract will be executed in that manner, without the need for third parties like lawyers, auditors, banks, witnesses, and governments. Now, why do the smart contracts need a blockchain? So smart contracts require witnesses in the form of honest nodes operating in the network. So you may see the word anonymous, but yeah, that's mostly in public blockchains. In private blockchains, it's wholly possible to identify which node it belongs to who. So the problem is node may not necessarily be honest. And smart contracts require what we call a Byzantine fault-tolerant environment. So consensus on the network must be reached, even though there's failure of the nodes. Imagine if one node fails among a sea of 1,000 nodes and the entire system breaks down. That doesn't make sense, right? I'd rather use AWS. So in essence, smart contracts are ensured this consensus to a higher degree through the blockchain. So now, let's get to the good stuff, smart contract attack vectors. So how many of you are developers coded in any form of language before? Another raise of hands? That's great, because up for you, I got a code. So over here, I have a smart contract that basically transfers money. So I'm taking an array of receivers, and this is the value that I want to send to these receivers. So maybe I'll just give you some time, maybe about 20 seconds to see, is there any fault in the contract? So we have count, we initialize count, which is the receivers.length, so how many receivers there is. We have the amount, which is basically we get the number of receivers multiplied by the value that we want to send. We require the count to be more than 0, less than 20. This is an arbitrary statement to ensure some sort of required stuff. Then we require the value must be more than 0, so that we cannot send $0. And the balances of the message sender. So this means that the person calling this function must have the balance, the account must have a balance that is greater than the amount that it's trying to send out. So the rest of it is really just the code to execute the transfer. So does anyone see a potential problem in this code? Sorry, sir? Yes, sir. So it's exactly that. So there could be an integer overflow. In this case, for the uninitiated, the integer overflow is when someone puts in a value that exceeds the limit and then it becomes something else. In this case, it wraps around. So in Solidity, which is the Ethereum programming language, uints with unsigned integers have a max value of 2 to the power of 256 minus 1. Now, what happens in this contract if I call 2 to the power of 256 over 2, which is 8 to the power of 16 to the power of 63, with 2 addresses? What happens, let's run through that, okay? So we have 2 people. The value is legit because now we have a huge amount of value over here. It passes the first requirement because the number of people we send is 2, which is more than 0, less than 20. The required value is where the magic happens. So yes, the value is huge. It's more than 0 for sure. But the amount that I'm sending, because of integer overflow, is going to wrap around. It becomes 0. And it passes this check because I can call this with 0 money. And then I send money to 2 different receivers with this huge amount of coins, for example. So that is a flaw in the smart contract that not everybody can catch. So let's talk about timestamp dependence. So everything in the blockchain, especially for smart contracts, is deterministic. At least in Ethereum, it is deterministic. So it is very, very dangerous to attempt pseudo-random number generations via block timestamps. In this case, what an attacker can do is they can determine the random variable before you do, and then just pass in as a parameter to execute the function. So over here, the pseudo-random number generation here is, what I do is I convert the block hash number to an integer, and then I basically use that, I factorize this, and then I get a binary number 1 or 0. So 1 or 0 will determine heads or tails. So on a very superficial level, we can see that, hey, this looks like a very good way to do heads or tails. But actually, what an attacker can do is they can determine this beforehand and write an automated script to input the value so that they can they always get the value right. So another code over here, we have an auction contract which has a highest. So this basically saves the address of the highest bidder. Address, you can think of it as your username, for example. So every individual should have at least one address, and this address will correspond to an account. So the highest bid is also safe. So the person calling this will make a bid. Message.value is the amount of money that is attached to this function call. So if the message value, that means if the money that I'm sending to, the amount that I'm bidding is less than the highest bid, I throw an exception. If there's no highest bid, then I go and, if the highest bid is, not equals to 0, then I transfer. So what this does, right, is basically if I have a new highest bid, I will transfer the money over to the previous highest bid. And then I save the new highest bid address and value. So in this case, this is like what we call a king of the hill. So if let's say I want to be the king of the hill, I send a certain amount, maybe $100. And until someone sends $200, my address will be saved here as the highest bidder. And if someone else bids a higher amount, then my money comes back to me. So can anyone see a problem with this contract? Sorry, sir? Something like that, sir. Very close. So the answer is that there could be a denial of service. So in this case, when I conduct a transfer, so when this contract conducts a transfer to another address, smart contracts have to indicate if they are payable by nature. So if a contract is payable, it means it can receive money. However, if let's say I write a contract that can send money but not receive money, I can send money, I can become the highest bidder, but because my contract cannot receive money, no one will ever be able to displace me as the king because this function will fail. So in this case, this is useful in terms of auctions. If let's say the code is coded badly like this, without proper withdrawal patterns, then auctions can fail because I just need to bid one time and then I make sure that my contract cannot receive any money. And then I win the auction automatically. So there's this thing called the re-entrancy attack. So a re-entrancy attack can be think of as a recursive call. So what happens is over here, the magic over here is when right, is when a payment is made, right, it always calls the function, fallback function, which is the function that allows payment of the other contract. But the contract can equally call the payment again. So in this case, if you were to look at this line over here, so game originator will transfer the bet amount to someone, correct? To the game or something. But the thing is, if I code the fallback function, if I code the contract to upon receiving payment, I call this exact function again. What happens is that it's going to be a recursive call. It's going to send and send and send, and because there's no update over here that tells the people that, hey, I already sent this, I already completed this transaction, it's just going to recursively call and wipe out the account. So this actually occurred before in what is known the DAO hack, which caused a USD $60 million worth of Ether. At that time, it comprised of 15% of all Ether in the network. So solutions can be, you can set a Boolean you can set a Boolean over here, for example, or you can even deduct the transferable amount from the balances before conducting the transfer. So that's one way to do it. We can do phishing as well using transaction.origin. So this is very Ethereum specific. Perhaps due to lack of time, I'll just skim through this. So what happens is, what I have here is I have a wallet. And the problem here is using transaction.origin because this wallet has a function transfer to. So you have understanding the nuance of smart contracts is important. When a contract calls another contract, it is a message sender. When, however, the person calling the person who pressed the button in the first place, that guy is the transaction owner. So what happens is I can write an exploit that basically calls the wallet. I insert the message sender of the wallet, and then I transfer. So what happens is, is that it will come here and it will pass. So even though it's not supposed to pass, because I coded the exploit in such a way that I manipulate the address over here, it will take the address, call the amount, verify, and then it will succeed. So this is kind of a phishing in the sense that I am impersonating the wallet, even though I'm not really the wallet. So bad coding has left many applications and providers vulnerable to attacks. In this case, I'm going to talk about the parity wallet attack, which in the first attack, which you see here, cost them 150 million USD. And they caught 2 occasions. So the second attack, they cost 31 million. So let's go through this. Over here, we can see that when a wallet is called, right, it does the normal stuff, they put the deposit, and the danger here is actually in this method called delegate call. So delegate call is called in the wallet library method. And this is dangerous because delegate call essentially allows anyone, or it gives permission to anyone to manipulate your contract over here. And that is dangerous. Why? So what happens over here is that this person, by putting in, smart contracts receive information through hashes. So when I want to call a function, I get a function name, for example, init day limit. I get the name, I get the parameter, I hash it. And then I put it in, I put the first 4 bytes into the message data. And that's how functions are called in smart contracts. So what happened is I could just get an init day, what I could do is I get an init wallet, for example. And the damning thing, which is the one that caused this to fail, is that there is no check. Anyone can initialize a wallet. And that is not supposed to be. You should always check that the person who is calling the wallet is the owner of the wallet before you do anything. But in this case, they completely neglected to check who is the one calling this function. And as such, anyone in the world can claim ownership of this wallet. If you were to see, anyone in the world could actually initialize control of this wallet, and then they can execute money. So they were actually exploited, and it cost them 150 million. The second example over here, if you were to see, this function looks very familiar because they didn't patch it. So there's bad coding, there's bad coding practices. So what happened here is that in this case, money was not sent out. In the previous example, money was executed to transfer money from an address to, from the wallet to my address, for example. And I can even set how much value I want. In this case, no money was transferred. What happened was that this person didn't realize, or rather Parity didn't realize that their wallet library was in essence a wallet itself. They didn't realize that. So they called this hacker called the init wallet, took ownership of the entire wallet library, and then killed the entire library. And then basically everyone's funds were frozen because now no one could actually access this library because the address is hard-coded. So no one could access their funds and everyone's like, what the heck is going on? And that actually caused $31 million of Ether to be frozen. So that bad coding left them vulnerable to attacks, and what happened to Parity is they just gave up. They didn't do wallets after that. The short address attack should be my last attack on the smart contract platform. So what we see here, right, is that if you were to take some time to look at this contract, it looks very innocuous. Or innocuous, sorry. So what happens is I have a token, I initialize the token, and then as you can see, transaction.origin. So the person calling this contract will have a balance of 1,000 tokens. I am able to send coins to an address and send a specific amount of coins. This will return a boolean that determines whether it's sufficient or not. If it's insufficient, it returns false, for example. So if you were to see, can anyone see the potential danger in using this? It's not very obvious because the code isn't the problem. The compiler is the problem. So the fault here is in the way the virtual machine actually handles underflows. So what happened with underflows is that it pads it with zeros. So let's take, for example, the address over here. So let's say I have this address here, okay? And then the amount that I put in is 2. So what it interprets is, remember when I say about the message.data? This is what is sent to the message data. So you can see the address over here, and you can see the amount that is sent over here, correct? So what happens is this guy tried, what happens if I delete a 0 from this? Because I know that it will pad it with 0 eventually, right? So I remove a 0 from the last digit of the address. And the way the results were quite astounding. So the virtual machine essentially just padded it, they took the 0 from the address. And then they realized that this didn't fulfill the number of bytes required, so they padded it with 0. And that's a problem, because now you have 30 new coins generated from nowhere. I hope my calculation's right. It's a bitwise operator, arithmetic shift. So yeah, from nowhere you generate 30 new coins. And this is actually due to the way it's being compiled. So this is even in the case where the contract is written quite securely, the compiler itself is at fault. In today's world, we actually have a lot of other libraries like Web3, which actually catches this and ensures that the address is of a certain length before it passes on. If not, it returns an exception. But in this case, some exchanges, some cryptocurrency exchanges, they try to write their own compiler and they fail to catch this, and therefore attacks like this can happen. Oh, I have one more, sorry. So honeypots. So who knows what a honeypot is? So a honeypot is something that looks too good to be true, right? You see the honey, you stick your hand into the pot, and then you realize, oh shit, there are bees inside. So in this case, this contract looks very nice. So I have so what I have over here is I have a withdrawal method. So this has a check. So this check that the person calling the function is the owner, which I mentioned just now. So this one is secure. Command. So this address, again, it has a require method, secure. But this method over here, multiplicate, it doesn't have a require. I can take in address, and if the amount I send to this function is more than the balance of this contract, they will send to me the total amount, the balance plus the amount that I send over. So if the contract is $1 and I send $2 to the contract, it will send to me $3. It sounds very good, right? But can anyone see what's the problem with this? So the problem with this, honestly, people have fallen for this trap. Like, if you were to go on Etherscan, right, if you were to go to the Blockchain Explorer and check, people have tried to send a lot of money to this. The problem being that this balance, so when you send when you send Ether or when you send cryptocurrency or any form of value into a contract, the state is updated before the method is called. So in this case, this condition will always return false because the state will be updated. If I send $2 to a contract that has $1, the state will be updated. So this will be $3. This will be $3. So $2 will not be more than equal to $3. And therefore, it will always fail. And people have been scammed this way. So this is a honeypot. It looks very nice initially. People cannot see the fault and they try, but in the end they get burnt because they didn't do their proper due diligence or they didn't catch this. So now let's go on to blockchain attack vectors, which I will talk on consensus mechanism attack vectors. So blockchains, as we said, they are distributed. They have various ways of talking to each node. The problem being, how do I ensure that the network comes to consensus? How do I determine what is an honest node? And how do I determine how the network determines what is the truth? So, there's this thing called a 51% attack. So, if you were to see, this is like a chain of blocks. Therefore, blockchain, right? So, what happens is every block is validated and then thus generated through a concept called mining, which is depending on your hashing power. Basically, you can think of it like brute force. I have a specific hash, and until that hash is solved, I cannot generate a new block. That's a very simplistic view, but for the lack of time, let's just take it as it is. So, the problem with this is that whoever has more hashing power is more likely to generate a new block, because if, let's say I have 5,000 computers versus your one computer that both of us are running simulations trying to crack the hash, right? Chances are the 5,000 computers will crack the hash before you do. So in essence, the entity with the most amount of hashing power is said to have the highest chance of generating the next block. And in this case, the 51% attack basically means that if I have 51% of the entire hashing rate of the system, I have the majority chance of mining blocks. And that means that even though my transactions are invalid, even though I can forge invalid transactions or fraudulent transactions, I myself, with a 51% chance, I can mine that block, I can validate the block and add it to the blockchain. And this is why it's called a 51% attack. So, other stuff like the long-range attack in proof of stake for Ethereum basically does the same thing, but instead of hashing. So the thing about hashing is that it takes extremely long. So you can imagine it such that I can take maybe for the entire network, right? In Bitcoin, I think it takes 10 minutes to crack one block, for example. So if I were to try to mine a new chain, for example, so chains are dependent on, for simplicity's sake, you can see as chains were, the branch with the longest chain will be the source of truth. So in this case, the goal here is to really, if I was an attacker, I want to create the branch with the longest chain. In Bitcoin, for example, which uses hashing power, it's obscenely expensive to do it because of energy requirements. Someone estimated that in a day, the entire Bitcoin network uses more electricity than the entire of Norway, if I'm not wrong. In proof of stake, this is solved through wealth. So instead of using hashing power to try to crack a nonce and generate a hash, basically the person who staked, so it becomes like a betting game. So I say I'm going to stake $500 inside, and if the transaction is fraudulent, you can take away my $500. So this is how, and the concept is that the person with a majority stake, if I have 51% of the wealth in the network, I wouldn't want to attack my own system because the valuation will drop and I will lose money. So in this case, the problem here is that it is not computationally expensive to generate a new chain of blocks. In Bitcoin, with hashing power, yes, it is expensive due to energy and due to the sheer amount of hashing required. But here, because it's just wealth, I can just take, if I were to go back all the way, so let's say this was the original good chain, and I'm an attacker, I came back to this chain, and then I create a new branch. And then I just what, I'm gonna stake 100% or I'm gonna stake 100%, and because no one else will want to stake on my branch, because it's, at that point of time, it is a smaller branch, it's not the main branch. I'm gonna stake 100% of my coins, and I'm going to be elected as the miner all the time. So what happens is, because there's no computational requirement, I can produce a block every 0.00001 seconds. And in essence, I can quickly overtake the main chain in no time. So that is the long-range attack, which is mitigated through various methods like slashing, and it's only a worry if you're trying to create your own proof-of-stake consensus, naive implementations, basically. So trusted execution environments, so there are consensus that try to elect the validator through trusted execution environments, but as we know, it is vulnerable. So things like Meltdown, Spectre, and Foreshadow have already conducted speculative execution attacks that basically try to determine some values from the memory, and from there try to determine how they can actually bypass the randomness, the so-called pseudo-randomness in this trusted execution environment. So as usual, try not to generate pseudo-randomness using SGX, for example. They have already openly admitted that they are vulnerable. So my final part of the presentation will be topology attack vectors. So let's say you don't have a computer. You cannot write a smart contract to attack the network. You don't have hashing power, and you don't have an account on Ethereum. How else can I attack blockchain? I can use network topology, telecommunications. So, So the partitioning attack basically says that based on the concept that, all the nodes are interconnected through connections with each other. So Bitcoin has 8 connections. Wow. Bitcoin has 8 connections, Ethereum has 13. So if communication from the nodes are malicious, it can actually influence the data recorded maliciously. It can record false data. And if executed on a large enough scale, it can partition entire networks. And this requires a hijacking of what we call the autonomous systems or the border gateway protocol. So let me just give you an example. There should be a video. Yeah. How do I play this video? Yeah, it should play. Yeah. So, oh wow. Basically, yeah. Sorry. How do I play this video? Okay, so it should launch. So in step 0, you can see that every node is connected. I hijack the AS. I go and influence the border gateway protocol to come towards me. I partition the network by sending them by telling them that they should talk amongst themselves instead. So what happens is, through the border gateway protocol, I can influence the routing such that nodes will then, instead of talking to each other, right, I influence the routing such that they talk with each other. By partitioning entire networks, I can actually, it's no longer secure because nodes do not have the true state of the network. They are talking amongst their own small groups. Then in that case, who is the honest truth? We don't know. And in fact, as the attacker myself, I can influence the data that is being sent over as well. So that is a vulnerability in using telecommunications. My final attack that I'm going to present on is called the delay attack. So we can essentially delay deliveries out to blocks to up to 20 minutes, and the victim will be unaware of the most recently mined block. As such, we can see that the nodes in the network will be vulnerable to double spending, which is the concept that, for example, let's say I pay, maybe I pay someone $500 Sing dollars, and I'm supposed to receive 1 Bitcoin. So traditionally, the network will say that he sent me the 1 Bitcoin already. But what happens if I send him the $500, the 1 Bitcoin was originally transferred to me, but someone reverses the network or creates a new chain that determines the 1 Bitcoin was never sent to me. I wouldn't have ownership of that Bitcoin. It would go to someone else. And then I wasted the $500 sending to him. So that's called a double spending attack. So wasteful mining in the sense that I mine so hard, I generate a new chain, and in the end it's for nothing. So so let's have a look at how this happens. So basically, what happens is we have the normal communications. Attacker calls the get data, and then it sends the block 20 minutes after. So what happens is the block, instead of delivering it immediately, right, I wait for a certain length of time, and then I send it over. And then everything will be delayed by 20 minutes. And this can cause a lot of problems in the system. I can use it to put fraudulent transactions in, do wasteful mining, as I mentioned. So, So actually, this is actually a practical attack. So it already affects the Bitcoin network. In 2015, 8% of all Bitcoin nodes were already hijacked. And today, every month, 100 Bitcoin nodes are victims of such border gateway protocol attacks. So, I have come to the end of my presentation, and I will be open to taking questions. Thank you.
Thank you very much, Jorden. Are there any questions from the audience?
Yes, sir.
Hey, man, good talk. I didn't quite understand the BGP part, right? Because BGP, when we think of BGP, we think of an ISP misconfigures a BGP and half the internet goes off, or a whole bunch of stuff happens, right? You mentioned like 150 Bitcoin nodes get hit by the BGP attack.
Yes.
How roughly does that work? Yeah.
Okay, so what happens is, let me just show. So every Bitcoin, node, so we can see that these are all nodes, correct?
Yeah.
So what happens is that all these nodes communicate through each other through ISPs, correct? So they need IP addresses to connect to each other. But these IP addresses are housed by who? The internet service providers. And you can think of autonomous systems as maybe a group of one or more internet service providers. So that said, the point of vulnerability lies in the communication itself. So if I was the owner of, let's say I managed to hijack Singtel, for example, all IP addresses that is going through Singtel and going out of Singtel will be controlled by me. If I have the encryption key, I can decrypt, and I can go and change the data that is being sent. So, as we mentioned, there are Bitcoin nodes. Bitcoin nodes take up to 8 connections per node, correct? So that means over here, right, I have one, I connected to this, I connected to this, I can take up to 8 nodes. But what happens if, as the internet service provider, I send a message telling them to change their connection to this instead, or to talk to themselves instead in a small group? So the entire concept of blockchain is to be distributed. Everyone talks to everyone. But if I can partition it and I make them talk to their own small groups, right, then whatever they talk about in their small groups, right, whatever transaction is recorded inside, right, when it eventually go back to the main chain, right, when it eventually connects, because Bitcoin nodes, they will have a reset. They have to go back, they will reconnect back to the main chain. All transactions that occur in their small node are not the majority. They are only a small portion, and they are definitely not 51%. As such, every transaction that has been recorded inside here will all be rejected. And so this is a case of how the partitioner attack can actually cause wasteful mining, in a sense, because I've spent so much energy mine the blocks, and then it doesn't occur. And at the same time, if I send $100, this Bitcoin node sends to me 1 Bitcoin, and then what happens is go back to the main, connects back to the main network. And then I realized that my transaction was overridden because it was rejected by the consensus. Then that's a double spending attack. So that is how attacks like this have occurred before. And according to a research paper that I've read online, I can send it later. It actually 100 nodes, not 150, 100 nodes every month are subject to this kind of attacks. Yeah.
Okay, thank you very much. That's all we have time for now. So if you have any other questions, or if you can think of them later, please ask them to Jorden later, because he will be around. Now, just give it up one more time for Jorden.